Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, presents the conference. GPT, Generative Pre-trained Transformer. GPT drives cognitive synthesis and the trend toward homogenization that occurs when using large-scale language models. Generative Pre-trained Transformers, GPT, are a family of neural network models that uses the transformer architecture and is a key advancement in artificial intelligence, powering generative AI applications such as ChatGPT. GPT models give applications the ability to create human-like text and content, images, music, and more, and answer questions conversationally. Organizations across industries are using GPT models and generative AI for conda, text digesting, content generation, and search bots. A generative pre-trained transformer, GPT, is a type of large language model, LLM, that uses a specific neural network architecture to understand and generate human-like text. The theory behind GPT is built on three core pillars. Generative. The generative aspect refers to the model's primary goal, creating new content rather than just classifying existing data. Autoregressive prediction. GPT operates by predicting the next most probable word, or token, in a sequence based on all preceding words. Sequential generation. Once a token is predicted, it is added back to the input, and the process repeats until a complete response is formed or an end token is reached. 2. Pre-trained. The learning process. Before a GPT model can follow specific instructions, it undergoes a massive phase of unsupervised learning. Massive datasets. The model is fed billions of pages from the internet, books, and articles. Self-supervised learning. It learns the statistical structure of language, grammar, facts, reasoning, by trying to predict the next word in these texts without human-labeled help. Fine-tuning. After pre-training, models are often refined using reinforcement learning from human feedback, RLHF, to align their responses with human values and safety. 3. Transformer. The architecture. The transformer is the underlying deep learning engine, introduced in the 2017 Google paper Attention is All You Need. Self-attention mechanism. This is the brain of the model. It allows the GPT to attend to different parts of a sentence simultaneously to understand context. Decoder-only design. Unlike some transformers that use both encoders and decoders, GPT specifically uses a stack of decoder blocks optimized for generating text one step at a time. Parallel processing. This architecture allows the model to process large amounts of data in parallel, rather than one word at a time, making training much faster. The first person to predict and generate texts using mathematical models was the Russian mathematician Andrei Markov. In 1913, Markov published a pioneering study, where he applied Markov chains to analyze the first 20,000 characters of the verse novel Eugene Onegin by Alexander Pushkin. Key aspects of his work. Pattern analysis. Manually counted the frequencies of vowels and consonants, to show that the appearance of a letter depended on the previous letter. Statistical prediction. It established that, based only on the current state, one letter, the probability of the next state, the next letter could be calculated without the need to know all the previous history. Markov property. Markov introduced the idea that the future is independent of the past, given the present, a fundamental basis for today's natural language processing. Markov not only resolved a mathematical dispute over the law of large numbers and dependent events but laid the groundwork for modern technologies like large LLM and GPT language models. The text presents the summary of the life of the Russian scientist Andrei Andreevich Markov. His best-known contribution is theoretical work in the field of stochastic processes known as Markov chains, which today are considered an essential tool in disciplines such as economics, engineering, operations research, and many others. In probability theory and statistics, a Markov process is a time-dependent random phenomenon for which a specific property is fulfilled. The Markov property, or without memory, is one for which the conditional probability about the present, future, and past state of the system is independent. The most practical importance is the use of the assumption that the Markov property is valid to construct a stochastic model for this process. it is a simple way to introduce statistical dependence, in such a way that it allows the strength of the dependence of the different delays to decrease as the delay increases. The term Markov chain is often used to imply that a Markov process has a discrete state space, infinite or countable. Normally, a Markov string would be defined for a discrete set of periods, such as a discrete time Markov chain, although some authors use the same terminology where time can take continuous values. We can talk about different definitions about the first-order Markov processes. States, the conditions in which an entity or possible events are found. Trials, repeated occurrences of an event being studied. Transition probability, the probability of moving from state I to state J in a transition or period. Markov, first-order, processes, to be used as models of physical or economic processes, must have a series of characteristics. The probability complies with the Markov principle. Existence of a finite number of states. The probability must be constant with respect to time or period. The trials must be in equal periods. Markov decision process. Today, in artificial intelligence, it is the mathematical framework that underpins reinforcement learning, RL, that models an agent's sequential decision-making in a stochastic environment to maximize accrued rewards. According to Markov property, the future state depends only on the current state and action, not on the whole story. RL algorithms find an optimal policy, what to do in each state by learning from the states, actions, and rewards. The MDP is well understood when the state and the spaces for action are small. Bertzka's, 2007, and dynamic programming, PD, algorithms, such as value iteration, Bellman, 1957, and policy iteration, Howard, 1960, are standard techniques for calculating optimal policies. In large state space problems, exact DP is not feasible since computational complexity scales quadratically with the number of states. The development of GPT has been an extensive process in which many people have participated and many technical terms coexist. The first two topics are natural language processing and LLM, large language model. From these concepts, the problems of estimation of artificial intelligence with depth learning are developed. Natural language processing, NLP, is a branch of artificial intelligence that allows computers to understand, interpret, and generate human language, either in written or spoken form. It's the engine behind tools we use every day, such as machine translators, voice assistants, Siri, Alexa, and chatbots. NLP is traditionally divided into two fundamental areas. Natural language understanding, NLU, focuses on analyzing the meaning, intent, and sentiment behind sentences. Natural language generation, NLG, it is responsible for producing coherent text or responses that sound natural to a human. There are three main approaches to developing these capacities. Symbolic or rule-based, uses rigid grammar rules programmed by hand. It is useful for very specific tasks but does not scale well in the face of the complexity of real language. Statistical, relies on probabilities and patterns found in large volumes of text to predict the next word or rank content. Neural networks and deep learning, it is the current standard, using architectures such as transformers, the basis of GPT, to learn complex contexts and deep semantic relationships. For a machine to understand a text, it usually follows a process, pipeline, that includes tokenization, dividing text into smaller units such as words or pieces of words. Stemming and stemming, reduce words to their root, e.g., running to simplify the analysis. Grammatical tagging, pause tagging, identify whether a word is a noun, verb or adjective according to its context. Sentiment analysis, determine whether the tone of a message is positive, negative, or neutral. Named entity recognition, NER, identify names of people, places, or companies in a text. A large language model, LLM, is a type of artificial intelligence. LLM is an advanced artificial intelligence systems designed to process, understand, and generate human-like text by analyzing patterns in massive datasets. Built on neural network architectures, Primarily the transformer model, they use billions or even trillions of parameters to capture the complex nuances of language. Transformer architecture. Most LLMs use a transformer model. This model allows LLMs to process entire text sequences at once. Next word prediction. LLMs predict the most likely next word in a sequence. This is based on patterns learned during training. Parallel processing. LLMs use GPUs to train in parallel, which speeds up the process. How they work. Transformer architecture, introduced in 2017, this architecture allows models to process entire sequences of text in parallel rather than word by word, making training highly efficient. Self-attention mechanism, this is the brain of the transformer. It calculates how much attention to pay to every other word in a sentence to understand context, such as distinguishing if bark refers to a dog or a tree. Tokenization. LLMs break down text into smaller units called tokens, words or parts of words, which are then converted into numerical vectors that the computer can process. Training phases. Pre-training. The model learns general language patterns by predicting the next word in vast amounts of raw data from the internet. Fine-tuning. The general model is polished for specific tasks, like legal analysis or customer service, using smaller, specialized datasets. RLHF. Reinforcement learning from human feedback uses human rankings to align the model's outputs with human values and safety standards. LLM models support generative AI models as a preliminary step to machine learning and artificial intelligence models. Generative artificial intelligence, Gen AI, is a type of AI that can create new content, such as text, images, audio, video, and computer code, by learning from vast amounts of existing data. Unlike traditional AI, which typically focuses on identifying patterns or classifying data into existing categories, Gen AI uses those patterns to produce entirely original outputs that often mimic human creativity. Gen AI models use deep learning and neural networks. They are trained on large datasets to understand the structure of information. Transformers, these are the architecture behind tools like ChatGPT and Gemini. They use a self-attention mechanism to weigh the importance of different parts of input data to generate contextually relevant text or code. Diffusion models, these are commonly used for high-quality image generation. They start with random noise and gradually refine it into a coherent image based on a user's prompt. Generative adversarial networks, GANs, these have two neural networks that compete against each other. One generates data while the other tries to detect if it is fake, pushing the generator to create increasingly realistic results. Key risks and ethical concerns. Despite its benefits, Gen AI presents several challenges that require careful oversight. Hallucinations. Models can confidently present false or fabricated information as fact. Bias. AI can inherit and amplify societal biases present in its training data. Intellectual property. Ongoing debates surround the use of copyrighted material for training and who owns the resulting AI-generated content. Security. Concerns include the creation of deepfakes for misinformation and the potential for new types of cyberattacks. Generative AI technologies are causing radical changes in the business world, giving companies a competitive advantage. To adapt to rapidly changing market conditions, keep up with digital transformation, and produce more innovative solutions, companies have invested in Gen AI, as it accelerates and improves efficiency and decision-making processes, from understanding customer needs to product development and marketing strategies. Several technology-producing companies have taken on the role of integrating generative AI into corporate operations by linking them to their CRM processes. The introduction of transformers models in artificial intelligence has brought about a monumental shift in the way machines understand, process, and generate human-like data. Previously, AI relied on sequential processing methods that struggled with long-term context and computational efficiency. Today, transformers models serve as the backbone of the most advanced applications that we use every day. Understanding them requires analyzing the limitations of past technologies. Recurrent neural networks, RNNs, and long-term short-term memory networks, LSTMs, were the standard, but they process data word for word. This made them slow and prone to forgetting the first parts of a sentence. The advent of transformers neural networks eliminated the sequential bottleneck, enabling parallel data processing, becoming the driving force behind modern digital innovation. The origins of transformer models in artificial intelligence can be traced back to a landmark 2017 research paper by Google, researchers titled "Attention is All You Need." This paper introduced a novel neural network architecture that abandoned recurrence in favor of an attention mechanism. This change was a breakthrough in the evolution of machine learning algorithms, demonstrating that machines could understand the context of a word based on surrounding words simultaneously, rather than sequentially. As transformer models evolved quickly, researchers were aware that this approach is incredibly scalable. The development of transformer models allowed engineers to train systems with unimaginably large datasets using parallel processing. This efficiency allowed deep learning models to grow exponentially in size and capacity, laying the foundation for the sophisticated AI transformer technology that currently dominates the tech industry. Transformer models' essential components. Layer normalization stabilizes training by normalizing activations across features, which reduces internal covariate shifts and improves convergence speed. During training, this normalization prevents sudden changes in feature magnitudes, making the learning process more consistent. Residual connections allows information to bypass multiple layers, improving gradient flow and preventing information loss. These connections are crucial in deep transformer stacks, where they ensure original information remains intact, and help mitigate vanishing gradient problems. Self-attention mechanism allows the model to consider all words in a sequence simultaneously, focusing on the most relevant ones regardless of position. Unlike sequential RNNs, it processes relationships between all words at once. Positional encoding. Since transformers don't process input sequentially, positional encoding preserves word order by adding positional information to word embeddings. This encoding uses sine and cosine functions. Multi-head attention. This feature applies self-attention multiple times in parallel, with each attention head learning different linguistic patterns. Some heads might focus on syntax, subject-verb relationships, while others capture semantics, word meanings. These parallel outputs are then concatenated into a unified representation. Feed-forward layers. Each transformer block contains feed-forward neural networks that process attention outputs. These consist of two connected layers with an activation function between them, that enhance feature representation by transforming the attention-weighted input. The encoder's job is to read the input data, like a sentence in English, and map it into a continuous mathematical representation, capturing all its contextual nuances. The decoder then takes this rich mathematical representation and generates the desired output, like translating that sentence into German. While some modern models use only the encoder, like the BERT model, or only the decoder, like GPT models, this fundamental two-part structure was crucial to the initial success of the architecture. The original transformer was built using an encoder-decoder structure. The encoder's job is to read the input data, like a sentence in English, and map it into a continuous mathematical representation, capturing all its contextual nuances. The decoder then takes this rich mathematical representation and generates the desired output, like translating that sentence into French. While some modern models use only the encoder, like the BERT model, or only the decoder, like GPT models, this fundamental two-part structure was crucial to the initial success of the architecture. How the transformers model works? The transformer model consists of an encoder and decoder, both built using multiple layers of self-attention and feed-forward networks. Input processing: the input text is tokenized and converted into word embeddings. Positional encodings are added to maintain word order information. Encoder takes input embeddings and applies multi-head self-attention. Utilizes positional encodings to maintain word order. Passes information through feed-forward layers for processing. Self-attention mechanism: the self-attention mechanism allows each word in a sentence to focus on other relevant words dynamically. Multi-head attention: instead of a single attention mechanism, multi-head attention allows the model to capture different relationships within the input. Feed-forward neural network. Each encoder layer has a fully connected feed-forward network that processes attention outputs. Decoder. Receives encoder output along with target sequence. Uses masked self-attention to prevent looking ahead. Combines encoder-decoder attention to refine output predictions. Improving Language Understanding by Generative Pre-training is the seminal paper published by OpenAI in June 2018 that introduced the first Generative Pre-trained Transformer, GPT-1. The paper demonstrated that a single, task-agnostic model could achieve high performance across a wide range of natural language understanding (NLU) tasks by following a two-stage training procedure. The model uses a semi-supervised approach consisting of two phases. Unsupervised pre-training. The model is trained on a large, unlabeled corpus to predict the next word in a sequence. This stage allows the model to learn grammar, world knowledge, and long-range dependencies. Supervised fine-tuning. After pre-training, the model is adapted to specific downstream tasks, such as sentiment analysis, question answering, or textual entailment, using smaller, labeled datasets. Task-specific input transformations. For some tasks, such as text classification, the model can be adjusted directly with fine-tuning. Other tasks, such as answering questions or textual implications, have entries structured as ordered pairs of sentences or triples of documents, question and answer. Since the pre-trained model, GPT-1, was trained with contiguous sequences of text, some modifications are required to apply it to these tasks. Previous work proposed learning task-specific architectures about transferred representations. This approach reintroduces a significant amount of task-specific customization and does not use transfer learning for these additional architectural components. Instead, a walkthrough-style approach is used, where we convert structured inputs into an ordered sequence that GPT-1 can process. These input transformations avoid making extensive changes to the architecture between tasks. Below is a brief description of these input transformations, that include adding randomly initialized tokens, S&E. Textual implication. For implication tasks, we concatenate the sequences of the P premise and the hypothesis H tokens, with a delimiter token, less than greater than between them. Similarity. For similarity tasks, there is no inherent order of the two sentences being compared. To reflect this, the input sequence is modified to contain both possible sentence orders, with an intermediate delimiter, and each is processed independently to produce two sequence representations that are summed item by element before being fed into the linear output layer. Answers to questions and common sense reasoning. For these tasks, GPT-1 selected a Z context document, a Q question, and a set of possible fake answers. We concatenate the context document with the question for each possible answer, adding a delimiter token. GPT-1 independently processes each of these sequences and then normalizes it using a softmax layer, to produce an output distribution on possible answers. Summary of the GPT workflow. Tokenization. Your prompt is broken into tokens, chunks of characters. Embedding. Tokens are converted into numerical vectors that represent their meaning in a multidimensional space. Positional encoding. Because transformers process data in parallel, positional markers are added so the model knows the order of the words. Processing. The data passes through multiple layers of self-attention to determine the significance and context of each word. Softmax layer. The final layer produces a probability distribution to pick the next most likely token. From ANN to GPT models, tracing the evolution of AI language models. In 1998, the LeNet 5 architecture was first presented in the article Gradient-Based Learning Applied to Document Recognition by Jan LeCun et al. They showed that convolutional neural networks are effective for handwritten digit recognition tasks. The figure shows an example of an artificial neural network with 8 input units, 4 output units, and 2 blocks of size 2 memory cells. The figure shows the transformer architecture and training objectives. The figure at right shows the input transformations for fine-tuning on different tasks. All structured inputs are converted into token sequences to be processed by the pre-trained model, followed by a linear plus softmax layer. 4 steps are followed. classification, entailment, similarity, and multiple choice. Two approaches are considered: race in answers to questions, and multi-NLI in textual implication. The figure illustrates the performance of the multi-NLI and race as a function of the number of layers transferred. We observe the standard result that transferring embeddings improves performance, and that each transformer layer provides further benefits up to 9% for full transfer on multi-NLI. This indicates that each layer in the pre-trained model contains useful functionality for solving target tasks. The right figure shows the evolution of zero-shot performance on different tasks as a function of LM pre-training updates. Performance per task is normalized between a random guess baseline and the current state of the art with a single model. Attention is all you need, published by Google, is the key paper of the actual GPT. Prior to GPT, recurrent neural networks, short-term memory, and recurrent neural networks with blocks had established themselves as cutting-edge approaches in modeling sequences and transduction problems, such as language and machine translation. Since then, numerous efforts have continued to push the boundaries of recurring language models and encoder-decoder architectures. Recurrent models factor the calculation along the symbol positions of the input and output sequences. By aligning the positions with the steps in the calculation time, they generate a sequence of hidden states, based on the previous hidden state and the input for the last position. This inherently sequential nature prevents parallelization in training, which becomes critical in longer sequences, as memory limitations limit clustering between examples. The fundamental constraint is sequential calculation. Attention mechanisms have become an integral part of modeling sequences and transductions in various tasks, allowing dependencies to be modeled regardless of their distance in input or output sequences. In all but a few cases, such mechanisms are used in conjunction with a recurring network. The authors propose the transformer, a model architecture that avoids recurrence and relies entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly greater parallelization and can reach a new state-of-the-art in translation quality after being trained for just 12 hours on 8P100 GPUs. Encoder and decoder stacks. Encoder. The encoder is composed of a stack of 6 identical layers that have 2 sublayers. The first is a multi-head self-attention mechanism, and the second is a fully connected and positioned simple direct feed network. A residual connection is employed around each of the 2 sublayers, followed by their layer normalization. That is, the output of each sublayer is the layer norm, x plus sublayer x, where sublayer, x, is the function implemented by the sublayer itself. To facilitate these residual connections, all sublayers of the model, as well as the embedding layers, produce outputs of dimensioned model equal to 512. Decoder. The decoder is also made up of a stack of 6 identical layers. In addition to the 2 sublayers in each encoder layer, the decoder inserts a third sublayer, which performs multi-head attention on the output of the encoder stack. Like the encoder, residual connections are employed around each of the sublayers, followed by layer normalization. The self-attention sublayer in the decoder stack is modified to prevent positions from paying attention to the following positions. This masking, combined with the fact that the output inlays are shifted at one position, ensures that predictions for position I can only depend on known outputs at positions smaller than I. The figure shows the transformer model architecture that follows this overall architecture using stacked self-attention and pointwise, fully connected layers for both the encoder and decoder. Most competitive neural sequence transduction models have an encoder-decoder structure. The encoder maps an input sequence of symbol representations to a sequence of continuous representations. Given the continuous representations, the decoder then generates an output sequence of symbols one element at a time. At each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. The transformer follows this overall architecture using stacked self-attention and pointwise, fully connected layers for both the encoder and decoder, shown in the left and right halves of the figure, respectively. An attention function can be described as mapping a query and a set of key-value pairs to an output, where the query, keys, values, and output are all vectors. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. The figure shows the scale dot product attention. The input consists of queries and dk dimension keys, and dv dimension values. The scalar products of the query are calculated with all the keys, each is divided into the square root of dk, and a softmax function is applied to obtain the weights of the values. The attention function of a set of queries, packaged in the Q matrix, is calculated simultaneously. Keys and values are also packaged in K and V matrices. The figure shows the multi-head attention consists of several attention layers running in parallel. Instead of performing a single attention function with keys, values, and dimensional queries from D models, we find it beneficial to linearly project queries, keys, and H values times with different learned linear projections dk and dv, respectively. On each of these projected versions of queries, keys and values we then perform the attention function in parallel, yielding dv dimensional output values. GPT is an advanced deep learning model, designed to comprehend and create human-like text based on the patterns it picks up after learning from vast amounts of text dataset during the pre-training phase. Key characteristics. Generative GPT can develop coherent and contextually relevant text based on the given prompt, ranging from a few words to entire paragraphs. Based on the prompts, GPT can produce responses based on various tones and styles, variations or a continuation of the prompt. Even a slight change in the prompt guarantees a different response generated by GPT. After all, GPT's generational capability stems from the context it detects from the prompt. Pre-trained. The pre-training phase is a pivotal point where GPT gains language understanding by predicting the next word in sentences. This step enables it to understand grammar and syntax and gain word knowledge. After this pre-training phase, GPT can be fine-tuned to perform specified tasks. Overall, the objective of pre-training is for GPT to learn the intricacies of language from large datasets. Transformer. GPT is based on the transformer architecture, a type of neural network architecture that excels at processing sequential data, such as sentences, phrases, paragraphs and so on. Due to this ability, combined with the architecture's efficiency, the transformer architecture is currently the most widely adopted architecture for multiple natural language processing, NLP, tasks. From GPT-1 to ChatGPT, evolution of the Generative Pre-trained Transformer. In recent years, AI has come to the forefront of technological innovation, and among its most impressive feats is natural language processing, NLP. The Generative Pre-trained Transformer, or GPT, series by OpenAI stands as a testament to how far NLP has come. Let's embark on a journey from GPT-1 to the current marvel, ChatGPT, and witness the evolution of a technology that's transforming our digital conversations. GPT-1, the Genesis. Launched in June 2018, GPT-1 was the first in a series that aimed to revolutionize machine understanding of human language. With 117M parameters, it was trained on the book's corpus dataset. GPT-1 showcased the potential of transformers, a novel type of deep learning model, in handling a range of NLP tasks without task-specific training. GPT-2, the breakthrough. Scaling up. The world took notice when OpenAI introduced GPT-2 in February 2019. Boasting 1.5 billion parameters, this model was a giant leap from its predecessor. OpenAI initially withheld the full model, citing concerns about potential misuse. GPT-2 demonstrated capabilities in tasks like translation, question answering, and even rudimentary reading comprehension. Its ability to generate coherent, diverse, and contextually relevant paragraphs of text was particularly striking. GPT-3, the game changer. Deep learning breakthrough. 2020 witnessed the release of GPT-3, the third iteration, and it dwarfed its predecessor with a whopping 175 billion parameters. Its vast scale and extensive training on diverse internet text allowed for unprecedented capabilities. GPT-3 could draft essays, answer questions, create poetry, and even code in Python. The model's adaptability led to a myriad of applications, from content creation to customer service bots. ChatGPT, fine-tuning excellence. Conversational mastering. Building on the foundation of GPT-3, ChatGPT was designed with a specific focus on improving conversational abilities. By fine-tuning GPT-3 on a mixture of licensed data, data created by human trainers, and other sources, ChatGPT showcased a nuanced understanding of user prompts. This iteration was a nod to the growing demand for chatbots and conversational agents in various industries. GPT-4, Generative Pre-trained Transformer 4, is an advanced artificial intelligence model developed by OpenAI, officially launched on March 14, 2023. It distinguishes itself from its predecessors by being a multimodal system, which means that it can process and understand both text and images to generate detailed responses. Key capabilities. Multimodality: you can analyze graphics, photos, and documents with images to solve complex problems. Larger context window: supports entries of more than 25,000 words, making it easier to analyze long texts and lengthy conversations. Advanced reasoning: has demonstrated superior performance on academic and professional exams, such as advocacy tests or advanced math, and enhanced creativity: uses more natural language, metaphors, and can adopt specific writing styles more accurately. The table specifications of GPT models shows the following data: model name, year released, architecture, and number of parameters. The speed of growth of the number of parameters is impressive. To solve the model, it requires high computational power. During the 2010s, improved machine learning algorithms, more powerful computers, and an increase in the amount of digitized material allowed for an AI boom. Separately, the concept of generative pre-training, GP, was a long-established technique in machine learning. GP is a form of self-supervised learning wherein a model is first trained on a large, unlabeled dataset, the pre-training step, to learn to generate data points. This pre-trained model is then adapted to a specific task using a labeled dataset, the fine-tuning step. The transformer architecture for deep learning is the core technology of a GPT. Developed by researchers at Google, it was introduced in the paper Attention is All You Need, which was released on June 12, 2017. The transformer architecture solved many of the performance issues that were associated with older recurrent neural network (RNN) designs for natural language processing (NLP). The architecture's use of an attention mechanism allows models to process entire sequences of text at once, enabling the training of much larger and more sophisticated models. Since 2017, available transformer-based NLP systems have been capable of processing, mining, organizing, connecting, contrasting, and summarizing texts as well as answering questions from textual input. GPT, a regression model. A small example of the power of computation is the case of regression models, which comes from genetics and was popularized by Sir Francis Galton in the late 19th century, with the publication of Regression Towards Mediocrity and Hereditary Stature. Today it is one of the fundamental techniques of predictive AI, parameter identification, but its concepts and limitations have not changed. They are: the number of observations must be greater than the number of parameters to be adjusted. The greater the number of parameters, the better models are generated in terms of goodness of fit, and if the number of observations is greater than the parameters, there will be redundant observations, which if used in the regression will produce confusion in the results to be obtained. In the origins of computing, the problem was the observation storage capacity, the power required to execute the process, that depending on the methodology, requires the inversion of a matrix of the size of the observations. With these constraints, estimating a model of thousands of parameters was a challenge. With the progress of computation, also evolved methodologies, estimation algorithms, until today to the conjunction of computing power and algorithmic power, which gives direction to the effective application of GPT models, which in practice permanently estimate models of hundreds of thousands, or millions of parameters. In the same way, will grow the power of prescriptive AI. Normally, in regression models, one of the main concerns is the sample size. Due to its smallness, this leads to low efficiency measures for regression quality indicators. But in GPT everything is different. Tech companies like OpenAI, considering that everything is on the web, made the decision to digitize the public content of the web to improve accuracy with an ever-growing sample. The growth in the number of parameters is directly related to the sample size. With this policy, GPT will have larger and larger public samples, require more parameters, and the day will come when all the available sample will have been consumed. Over time, the new sample content does not add value, as it corresponds to roughly duplicate data. What will happen that day? In theory, public GPT would have a universal model of known data that can no longer grow. ChatGPT, produced by OpenAI, is the state-of-the-art commercial artificial intelligence GPT. Is ChatGPT a neural network? Yes, it is. ChatGPT is a natural language processing model that uses a neural network to power its understanding and conversational responses to users' text prompts. Specifically, ChatGPT works with a large language model, LLM, called GPT-3, developed by OpenAI and which has 175,000 million parameters. This is due to the current computational power and the great availability of data on the web. ChatGPT uses a feed-forward neural network as well as a normalization layer to generate its human-like responses. The feed-forward neural network applies a nonlinear transformation to the input stream, ensuring that the model can learn complex patterns in each dataset. The normalization layer stabilizes this training process by making sure that the input values have a relative scale size. It uses a machine learning technique, called fine-tuning, to ensure it responds to prompts accurately. However, it should be noted that, like any predictive method, it meets certain basic characteristics. You can set the accuracy of what you predict for the sample. In a regression process, this precision is called R-squared. As the number of parameters increases, the accuracy increases. But too many parameters lead to problems of overestimation. Accuracy depends on the quality of the sample, it can never explain what is not in the sample. ChatGPT, produced by OpenAI, is the state-of-the-art commercial artificial intelligence GPT. Is ChatGPT a neural network? Yes, it is. ChatGPT is a natural language processing model that uses a neural network to power its understanding and conversational responses to users' text prompts. Specifically, ChatGPT works with a large language model, LLM, called GPT-3, developed by OpenAI and which has 175,000 million parameters. This is due to the current computational power and the great availability of data on the web. ChatGPT uses a feed-forward neural network as well as a normalization layer to generate its human-like responses. The feed-forward neural network applies a nonlinear transformation to the input stream, ensuring that the model can learn complex patterns in each dataset. The normalization layer stabilizes this training process by making sure that the input values have a relative scale size. It uses a machine learning technique, called fine-tuning, to ensure it responds to prompts accurately. However, it should be noted that, like any predictive method, it meets certain basic characteristics. You can set the accuracy of what you predict for the sample. In a regression process, this precision is called R-squared. As the number of parameters increases, the accuracy increases. But too many parameters lead to problems of overestimation. Accuracy depends on the quality of the sample, it can never explain what is not in the sample. Prompt engineering is the skill of writing clear instructions for an AI system that allows it to produce exactly what you need. Prompt engineering. Prompt engineering is the discipline of designing, optimizing, and refining the inputs, instructions or prompts, given to an artificial GPT to obtain accurate and high-quality results. It is considered both an art and a science, as it combines linguistic clarity with a technical understanding of how language models, LLMs, process information. There are several strategies to improve AI responses. Zero-shot prompting, asking for something directly without giving previous examples. Few-shot prompting, provide the model with some examples of the desired task so that they understand the pattern. Chain of thought, asking AI to think step by step to solve complex reasoning problems. Role prompting, assign a specific role to the AI, when acting as a marketer, to adjust its tone and perspective. Prompt chaining, breaking down a complex task into several steps, using the output of one prompt as input for the next. Prompt engineering important techniques. Arithmetic validation, when math becomes truth, algorithmic protocols, replaces trial with steps, granular documentation, force proof of execution, chain of thought, make reasoning visible, thought tree, explore before committing, react, reasoning plus action loops, self-consistency, generate multiple paths, choose the best, meta prompting, let the AI design its own instructions, zero shot versus few shots, when examples help, when they hurt, and reasoning models, why they are different. Using generative pre-trained transformers. Public GPT versus enterprise GPT. As technologies like ChatGPT and DeepSeek become household names, companies are increasingly exploring how generative pre-trained transformer models can revolutionize their business processes. However, there is a significant distinction between enterprise GPT and public GPT models that every executive should consider. There are 5 main differences. Public GPT, 5 main differences. Data security and privacy. These models operate on external servers, which poses risks when processing proprietary or sensitive information. Data governance is often a concern, especially in highly regulated industries. Implementation cost and operational costs. Lower upfront costs with subscription or usage models. However, unpredictable costs can arise as usage grows. While operating costs may seem lower, a lack of custom automation and efficiency improvements could result in hidden costs over time. Customization and control. It is based on public data and pre-trained insights. Adaptation to specific business contexts is limited, making it difficult to achieve full operational efficiency. Successful implementation, risk management, and return on investment. It is easier to deploy for general use, but enterprise adoption requires additional layers of development, which can introduce risks and dependencies on third-party solutions. ROI is often indirect and less predictable, as these models are not designed for specific business cases. Sustainability and long-term impact. While effective for immediate needs and experimentation, the sustainability of models in a business context is limited. The need for constant adaptation, compliance issues, and a lack of custom optimization all affect long-term strategic alignment. Enterprise GPT, 5 main differences. Data security and privacy. It operates in a secure, enterprise-grade environment, ensuring that sensitive data never leaves the organization's control. Fully customizable with internal data sets, aligning with compliance and regulatory needs. Implementation cost and operational costs. The initial setup and infrastructure investment may be larger, but customized solutions lead to a higher return on investment, ROI, in the long run. While operational costs include infrastructure maintenance, training, and upgrades, they are balanced with increased efficiency and optimized resource allocation. Customization and control. Enables deep integration with internal systems and applications. Custom models can be tuned with proprietary data to generate unique business insights and process automation. Control over the deployment environment improves operational consistency. Successful implementation, risk management, and return on investment. The implementation is backed by dedicated support, robust testing, and integration methodologies tailored to the business environment. Businesses can achieve a higher and more predictable ROI through increased productivity, a better customer experience, and streamlined operations. Sustainability and long-term impact. It offers a sustainable approach by enabling continuous learning and optimization within a controlled environment. As business models evolve, enterprise GPT adapts and stays aligned, contributing to long-term digital transformation. Public GPT versus enterprise GPT. While GPT models such as ChatGPT and DeepSeek offer an excellent entry point to generative AI, enterprise GPT represents a strategic leap towards the digital transformation of enterprises, as it is the basis for assessing whether the organization is ready for customized, secure, and scalable solutions that align with business objectives. For organizations looking to transform not only processes, but also generate a measurable return on investment, reduce operational costs, and build a sustainable competitive advantage, investing in enterprise GPT is a critical step. Generative Pre-trained Transformers. Public users of public GPT. Massification of ideas. A lot of ideas go into GPT, comes out one. GPT drives cognitive synthesis and the trend toward homogenization that occurs when using large-scale language models. In artificial intelligence, the synthesis funnel is the phenomenon in which many ideas enter and only one comes out. This is due to the architecture of GPT models. The process can be described as data compression. During its training, the model processes trillions of text fragments, ideas, facts, styles, and converts them into mathematical vectors or embeddings. Statistical prediction. Instead of choosing the right idea, the model calculates the answer with the highest statistical probability, based on the patterns it has learned, acting as a filter that discards the less common options in favor of majority statistical consensus. With this approach, creating a new idea is impossible. Noise removal. The synthesis process helps to control fragmented information, transforming disordered data into a coherent and structured narrative, but unique. Massification has critical side effects on diversity of thought and knowledge. Homogenization of thought. By favoring the most frequent patterns, AI tends to produce average or generic content, which dilutes individual creativity and minority voices. Creative illusion. Studies suggest that although GPT generates ideas quickly, most can be repetitive or similar, lacking the diversity that human critical thinking brings. Confirmation bias. The model is optimized to give answers that are satisfactory to the user, often leading to constant self-validation rather than challenging ideas with conflicting perspectives. GPT forgets that. For Henrik Ibsen, in scientific thought, the majority is never right. The phrase "the majority is never right" is a famous statement by playwright Henrik Ibsen, who argues that the dominant opinion often prioritizes comfort, conformity, or popularity over objective truth. Ibsen asserts that conventional wisdom, or popular consensus, is often flawed and that progress comes from minority and independent perspectives. He argued that an enemy of humanity is the majority, which is made up of ignorant people, who cling to social lies, suggesting that they take a long time to be right, if ever. Other important opinions are: Mark Twain, "Whenever you're on the side of the majority, it's time to pause and reflect." Leon Tolstoy, "What is wrong does not cease to be wrong because the majority participates in it." George Bernard Shaw, "The minority are sometimes right, the majority, on the other hand, are always wrong." Søren Kierkegaard, "The minority is usually made up of those who really have an opinion of their own, while the strength of the majority is illusory and based on blind following." Albert Einstein, "What's right isn't always popular, and what's popular isn't always right." In 2020 there was already an awareness that the impact of industrial revolutions could be negative, and that this is apparently still happening. Digital natives are the first children with a lower IQ than their parents. This originates in the scientific gap that is forming. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university, however, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. Now GPT is the intelligent, and super-fast, consultation of what is recorded on the internet, which limits many professionals to this knowledge. Optex GPT is the current research and development plus innovation project, based on artificial intelligence, focused on generating a new version of the Optex optimization expert system, fundamentally aimed at generating a new interface, for modelers and users, of Optex, based on GPT-type artificial intelligence. Optex GPT in a GPT enterprise application. Following the principles of Generative Pre-trained Transformer AI, Optex GPT will be the advisor that helps mathematical modelers, and professional users, when they require solutions in line with today's cutting-edge technology. Optex is focused on the implementation of artificial brains, conceived as a union of optimization models, with information systems. In the development and maintenance of high-complexity mathematical programming, Optex avoids the intensive use of resources for programming computers. The process of uploading Optex will be a more interactive activity through generative artificial intelligence, such as ChatGPT Omnichannel 4.0. In this way, the user will be able to communicate with the Optex model database, and use all the documents produced by HI for the management of the system. All through a conversation, out loud if you will, with Optex GPT. At the limit, if the user wishes, Optex GPT can perform the entire process in a single step, until the results are delivered. There is no need to store intermediate results. The basis of the Optex GPT conversation will be based on so-called prompting engineering, called by HI as the engineering of ideas. Optex GPT will be a specialized generative artificial intelligence to work in the Optex Optimization Expert System environment, which will be powered by mathematical models that exist in the current Optex database, and of all new models that will be introduced. Technical documentation that supports Optex, and the mathematical models developed, and general technical information. On the other hand, from this knowledge information, Optex GPT will help the user build new mathematical models. Several GPT models will be developed, in order to serve users with different levels of experience. The main product is the management of MES, Mathematical Modeling Information System. From the correct configuration of the MES, the modeler will be able to configure the required algorithms, link them together, and generate the computational code of their choice. Finally, she will be ready to run the multi-problem models. The data source for building a model can be the description of the real model, and/or the algebraic formulation, and/or pre-existing models in the Optex database. Another of the functions of Optex GPT will be aimed at supporting users in specific applications, to accompany them in the process of elaboration, or selection, of mathematical models, the loading of industrial databases, and the interpretation of the results. The main product is the management of IDIS, Industrial Data Information System. This work will be advised by Optex GPT, based on the data model of the IDIS database. This includes the verification of the validity of the database, considering the metadata of each of the fields of the tables. As an advisor, Optex GPT will have access to a database of documents, some generic and some specific, to facilitate the understanding of the company-wide optimization system by the user group. The image shows the connectivity of the Optex and Optex GPT databases. The Optex GPT database stores different types of documents oriented to the models and solutions that the user handles. Optex Expert System Database, Optex Manuals, User Application Manuals, manuals of the work carried out for the user, and technical documents such as papers. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.